Hi guys, and welcome to this video. Yesterday, or maybe today, depending on when you're seeing these videos, we were talking about initial values and rate of change. So I want to start off this video lesson with identifying the initial value and also the rate of change. So for all of these situations, I want to make sure that we got what we needed to get. So here's some scenarios. The cost of a school banquet is $95 plus $15 for each person attending. What is the initial value and what is the rate of change? Okay, so hopefully you recognized that the original cost is $95, so that's my initial value. And then for every additional person that comes along, $15 for each is my rate of change. Remember how we talked about at the end of last lesson, if it says for each, for every, per, those kind of words kind of help us determine if we have rate of change. The second situation says a sunflower was 12 centimeters tall when it was first planted. It has grown 0.6 centimeters per day. What's the initial or starting amount of this sunflower, right? When it was first planted, how tall was it? It was 12 centimeters. And how much did it grow every single day? That is its constant rate of change. It was 0.6 centimeters, again, per day. Our next situation says Ross spends $8 every day. He started with $200 in his account. So we want to find out the initial value. How much money did he start with? Well, he started with $200. So that must be the initial value. And he spends $8 every single day, right? The word each is appearing again. If he's spending money, his account is decreasing. 200 minus 8, 200, and then minus 8 again, and then minus 8 again, right? As every day passes. The next example says a phone starts with 95% battery, but loses 9% each hour. So how much does our battery start with? Well, it starts with 95. And then every single hour, no matter how much or how little you use it, it drops 9% each hour. Last example, a stable charges $10 per hour plus a $20 flat fee for horseback riding. Okay, so clearly we're talking about horses here. So we want to find the initial value. How much are we starting amount with, and the rate of change. It's a constant same number from hour to hour to hour in this context, right? So if we're trying to figure out the starting amount, no matter what, this stable charges $20 flat fee, regardless of what you're doing. And then after that, you have to charge the $20 to get in to do some horseback riding, and then you get to pay per hour. How much? $10 per hour. Again, where it says per, each, per, for each, right? All of these words right here help us to identify the rate of change. Excellent. So I really like that we've been starting off with some real world context instead of just jumping straight in to the purpose of this unit, which is a type of functions. It's linear functions, and it's based off of this idea where we have an initial value and we also have our constant rate of change, but it's going to look a lot different than these problems where there was that constant pattern of how things are constantly changing. And so I thought this was a cool way to start it off, right? Our constant rate of change, again, as a reminder, constant means the same every time. Rate of change from one to the next, how much is it changing, right? And our initial value was the starting amount after we kind of discussed those examples. Hopefully it's clear. So if we're talking about linear functions, a linear function is a function that produces a line, a straight line on the graph, just like we were talking about in the last lesson. Linear functions have two main parts or two main features to them. A constant rate of change like we said, which we're not going to use constant rate of change. What we use in the math world is what the constant rate of change is actually known as, and that is the slope. So that's one part of a linear function. The other part is the initial value, which is why I was spending so much time talking about these two parts. Now, we don't really call it initial value per se in math. We actually call this the y-intercept. Okay, so a line is made up of two main parts. The two main parts we've been talking about now, the constant rate of change, aka our slope, and the initial value, aka a y-intercept. So let's start breaking this down so it starts to make a little bit more sense and put it in a mathematical equation. So we have one of the most famous equations, arguably, in all of math is y equals mx plus b. It's right up there with Pythagorean theorem. Like, it's one of those things where you ask kids, hey, what do you remember? And they're like, y equals mx plus b. Couldn't tell you, but y equals mx plus b. So we want to break down what they mean so you do know what to say, right? Y is one of our variables in the context of this problem. And we know that y is a part of the range, aka an output value, right? And so I just want to remind us that y is a variable. It's the output, and that is what our equation is equal to. So y, our output, is equal to mx plus b. So we got to tell you, what the heck is m? What is x? What's b? So m, I don't know why, but in math land, m represents your slope of the equation, right? Or that constant rate of change. Or when we were looking at the graph, right? How much is it rising? How much is it going over? Is it going up or down so many? Is it going right or left how many? Depending on the graph. So we like to call this, you might have even heard it like this, rise over run. And I like to do rise with arrows going up and down, like what's my graph going up and down, and running going from left to right. X is another variable that we have. It's just going to stay there. So y and x are going to be in our equations. Y equals a number, x plus b. And remember that x's are input values. So we could actually plug something into the x and get out the y value if we were to evaluate. And lastly, we have b. Okay, b is our initial value. Or the mathematical term is our y-intercept. And when we're like b is a number, b could be positive, b could be negative, depending on the initial amount of money or whatever the context has to be in our problem, right? It could be money, it could be temperature, it could be so many different things. It could be number of cupcakes, right? But that's our initial value, our y-intercept. And we like to write our y-intercept as 0, b. I know it doesn't really ask for that right now, but that's a fact that we're going to stick with throughout the entire unit. So now that we have the idea of what the heck y equals mx plus b is, it's made up of two parts, our constant rate of change, aka the slope, and our initial value, aka the y-intercept, we can start to put some pieces together, right? So here's an equation. Y equals 2x minus 3. We have a table, and we can find our initial value and our rate of change. So just to start, before I go into the table, right, something I know straight away from breaking down the slope-intercept form is I know m is the slope straight away. And see how m is right in front of the letter x? I know 2 is going to be my slope. Similarly, b plus b minus b, whatever it happens to be, is the initial value, or our y-intercept. So automatically minus 3 is going to be my y-intercept. So I like to just fill in that part first. So my initial value is going to be 0, -3 as an ordered pair, or you can say y equals -3 would be appropriate for the y-intercept. And my rate of change is going to be 2, or 2 over 1, because I want like a fraction, rise over run. This means I'm going to go up 2 and right 1. Based on this information, I can start to graph. I can go to the y-axis is -3. That's right here, and put a dot. And then I can use my slope to start to plot some points on the graph. Since my slope is 2, from this point, I go up 2 and right 1. Put a dot there. And continue. Up 2, right 1. Up 2, right 1. Up 2, right 1, just based on following that pattern. And I have part of my line. When I run out of space, I like to go back to the start, back to my initial value. And to keep the pattern going, I'm going to do the opposite. Down to left, down to left. And you'll notice, like, if I go to the furthest left point, it's the same thing. If I went up to right 1, up to right 1, I'm in the same spot. And this is a perfect line. Like we said, a linear function forms a perfect line. So how does this tie into the table, right? Well, we can see that x is our input values and y is going to be our outputs. So we can practice evaluating functions and plugging in values for x and seeing what we get out for y. We'll start with our very first one that's given to us, the input of x being 0. So I'm going to plug that into my equation, right? Y equals 2 input 0 minus 3. Now I need to use the order of operations to finish solving. 2 times 0 is 0. Take away 3. That gives me my output value of -3. So 0, -3, 0, -3. Look at, that's right here. That is my y-intercept. Pretty cool. And now my table's empty. They didn't give me other inputs, but I can choose. So I can pick any numbers I want, right? Maybe I pick 1, maybe I pick 2, maybe I pick -1 and -2 just to see. But really, I could pick whatever numbers I want. And I would just apply the same idea. I'll start with my equation, y equals 2x minus 3. Instead of x, I'll plug in my input. So for here, it's -2. Use the order of operations to simplify and figure out my output. There's parentheses, there's no exponents. Now I need to multiply or divide from left to right. 2 times -2 is -4. Minus 3. This gives me my output of -7. Now let's take a quick look here. -2, -7, -2, -7. Oh, that's right here. That's that point over here, the far left one, the one that I just used the pattern. It's pretty cool. Now you could make a prediction. We could plug in -1, but look between the 0, -3 and -27, the green and the orange dots. What is my output going to be based on the graph at -1? What is the y value for my graph when x is -1? Or what I could ask you is, what is f of -1 going to be, right? I find -1, I go down to my graph, I look at the y. We can see from the pattern that that's -5, or 2 times -1 minus 3. -2 minus 3 gave us -5. And you could continue to plug these in for x is 1 and x is 2. Or looking at our graph, when x is 1, we get out -1. When x is 2, we get out +1. And so we can start to see how the equation and the table are related. The x The y-intercept is a starting point on our graph. It's where we start on the y-axis, and how the rate of change or our slope can really help us to get a good idea of what this graph is. Here's another example. Y equals negative x plus 4. First things first, we want to figure out what is our initial value and what is our rate of change, the slope. I just want to make sure I'm using the same colors. So pink for rate of change and initial value orange. Okay, so pink for rate of change. Rate of change is another word for slope, and slope was m. It was in front of x. This negative sign is my slope. Negative sign is my slope. And you're like, negative what? Well, -1, of course. And again, I like to write it as a fraction because it helps me. If my rate of change is negative, that means I'm going to go down instead of up. And I'm still always going to go to the right. So my slope is -1, or just negative. This is a hidden baby 1, right? -1. And my y-intercept is 4, or my initial value is going to be 4. So I can say y equals 4, or even better, I can give exact directions, x comma y, 0 comma 4. X is 0, y is 4. And I'm going to plot that right there on the y-axis. That's my starting point. Again, let's use my pattern. My slope is -1, so I'm going to go from the starting point, down 1, right 1. Here's a point. Down 1, right 1 from that next point. Down 1, right 1 from the last point. Down 1, right 1 from the last point. And just continue this pattern. Once I run out of space, I go back to the start and do the opposite. Instead of going down 1 right, I'm going to go up 1 left, up 1 left, up 1 left, up 1 left. And that is going to make sure that my graph decreases, that it stays going down. Because if I don't, my graph is going to look really wonky. Now that I have a picture of my graph, I can identify my y-intercept immediately. It's when x is 0, y is 4. When my input is 0, I get out 4. And I could certainly practice plugging in some values. Maybe I'll practice plugging in the positives here for this equation. When x is 1, I have negative parentheses plus 4. -1 plus 4, that's just literally -1 plus 4, or 4 minus 1, which is 3. And if I look at my graph and verify, when x is 1, do I get 3? When x is 1, is the height 3? It sure is. Cool. Let's practice plugging in 2. My original equation is -x plus 4, or negative parentheses plus 4. The x I'm plugging in, the value I'm substituting in for x, is 2. So I have -2 plus 4, or 4 take away 2, which gives me my output of 2. Let's verify that this is on the graph as well, right? 2 comma 2. When x is 2, y is 2. That's that point right here. Perfect. And so I could continue doing this and substituting in, or I could use my knowledge of how to evaluate a function given a graph. And if I was like, well, -1, when x is -1, what is the y? It's up there at 5. I could even go so crazy and I could say, hey man, what is -4? When x is -4, look up to the graph. How high is it? What's the height? And I could get 8. And it's the same thing if I plugged it in to the equation. I have a couple more examples, so hopefully this helps us feel a little bit better. What happens if our equation is y equals 2 over 3x plus 2? This one definitely feels different. This one feels a bit tricky. So we're going to start by identifying our rate of change, or the slope, right? Remember, that is the value in front of x. And you know what? It's actually easier if it's a fraction. It's 2 over 3. What this means is, since it's positive 2, we're going to go up 2. And since the denominator is 3, we're going to go right 3. But we need the initial value first. Where should we start? What is the y-intercept? Remember, that's what comes after the x. So if my y-intercept is 2, or better yet, 0, 2, I can start by plotting that point on my graph. X is 0 and y is 2 is right here on the y-axis. Now I can use my slope, or my rate of change, to begin plotting a graph from my starting point up to right 3. And from this next point up to right 3. Remember, it's got to be constant. From one thing to the next, it has to be the same. I'm going to run out of points. I'm going to go back to the start. And to maintain that pattern, I'm going to do the opposite for the bottom half. Instead of going up 2, I'm going to go down 2. Instead of going right 3, I'm going to go left 3. Down 2, left 3. I'm also running out of space. But now you can see when we go from left to right, my graph is constantly increasing at my slope. It's constantly from left to right going up to right 3, up to right 3, up to right 3. Every single time, and I'm on my graph. If I wanted to determine in my table where my y-intercept is, remember, that's 0, 2. So when x is 0, y is 2. I can prove it to you. Y equals 2/3 x plus 2. Remember, we wanted to plug in our input of 0. Anything times 0 is 0. 0 plus 2 is 2. So that's how I was able to get the y. And you can practice evaluating. Maybe we'll plug in 1 and see what we get. That one would be kind of weird. Y is 2/3 times 1 plus 2. This one's going to be gross. It's just 2 and 2/3. But you can see at 1, it's 1, 2, and it's a little hard to see here, but this isn't quite at the 3. Maybe my graph is a little off, my line's a little off, but this would be 2 and 2/3. If I want to make sure it's something perfect though, maybe I pick a red dot. Here's a red dot. When x is 3, what is y? I can use my graph to verify that it should be 4, but if I plug it in, y equals 2/3 x plus 2. Remember, I'm plugging in x is 3 into the equation. 2/3 times 3, that's 6/3, which I'm just going to write as 6/3 plus 2. But I know 6/3 is 2. So 2 plus 2 gives us 4, which is what we already had for the y. Perfect. Now you can choose a couple other values if you want to plug in, or for me, I'm just going to use the graph. Going to look at the other red dots on our graph. We have this one accounted for. What if x was -3? We can see that the y is 0. And if x is -6, we can see that the y is -2. We can also verify it with the math. So there's this worksheet that we have here for you. We have the equation. I'd like you to identify the rate of change, the initial value, draw a graph, and pick a couple points to plot on the chart. We have 9 problems for us to practice, and I hope that this was helpful for you, and you can start to see how those problems that we started with, whether it's the shirt at Target, going to the pumpkin patch, whatever it might be, is actually related to these linear equations. This assignment will be due on Canvas.